All right, so let's solve an example where we calculate the acceleration using the material derivative of the velocity. So let's consider a particular velocity field where the x component of velocity is given by kx and the y component of velocity is given by minus ky. That flow is called a stagnation flow. I think I might have shown you to you at some point in the class so far, but it doesn't matter. For the point of this example, just assume that this is some velocity field that you're given where the velocity depends on x and y. So note that when I look at this velocity field, it is a steady state velocity field, right? So the velocity doesn't explicitly depend on time at any given position, right? So the velocity depends on the position within the flow, but at any given position, it doesn't depend on time. That's what makes it a steady flow. So what I'd like to show you is that gives rise to a fluid acceleration. It's not going to turn out to be zero. So let's write out the acceleration using the material derivative. So the x component was partial u dt plus the convective derivative of that. So that's u du dx plus v du dy plus w du dz. Now, du dz is 0 because u does not depend on z, and w is also 0 because w does not depend on, or w is 0. If I look, the x component of velocity u doesn't depend on y, so that term is 0. And the time rate of the local time rate of change of u with respect to time is 0 because u does not depend on time at a given position x. And so you can evaluate ax and find that like the only terms that survive are u times du dx, which is just kx, k, which is k squared x. You can do the same thing for the y component of acceleration and write out its material derivative. So dv dt u dv dx plus v dv dy plus w dv dz. The z component terms are all 0 because there is no z component to velocity. It's steady state, so that term's 0, and v doesn't depend on x if you look at the dependence, and so that term is 0. And when you evaluate, you find that the acceleration in the y direction is just k squared y. And if you put that all together, that means that the local acceleration as a vector is just equal to basically k squared times the position within the flow, like the position vector.